Hello there, and welcome to Get Sleepy Science. I'm so glad you found your way here tonight. The sleeping brain is one of nature's most beautiful mysteries, a nightly journey through consciousness that we all take but rarely understand. Tonight, we'll drift gently through the science of sleep and dreams, exploring what happens inside your mind when the world goes quiet and your eyes close. Wherever you are right now, perhaps in bed with the lights low, or sitting in a comfortable chair as evening settles in, allow yourself to settle into this shared moment of stillness. Tonight, explore 100 remarkable truths about sleep, dreams, and the sleeping brain. From the waves of electrical activity that sweep through your neurons, to the strange worlds your mind creates in dreams, to the quiet repair work happening in every cell while you rest. If this thoughtful journey through the mind helps you slow down, a soft light helps more curious minds drift this way. Subscribing means another sleepless soul might discover this peaceful space tomorrow night. We'd be grateful, but there's no pressure at all. One sleepy soul at a time. For now, you don't need to do anything at all. Just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself drifting in a space of gentle curiosity, where facts become stories and stories become dreams. Now, if you're ready, let's begin our quiet journey through the mysteries of the sleeping mind. Now, if you'd like, close your eyes and take a deep breath. Imagine you're part of an endless stream of consciousness, where thoughts bloom and dissolve like waves, moving without boundaries, without destination. Let go of all limits. Let your mind drift through the space of awareness. And when you're ready, begin. Your brain doesn't actually rest when you sleep. This might seem surprising, but during certain stages of sleep, your brain is just as active as when you're awake, sometimes even more so. Modern brain imaging technology, particularly functional MRI and electroencephalography, has revealed that sleep is not a passive state of shutdown, but an active process of reorganization and restoration. Different regions of your brain take turns entering states of high and low activity throughout the night. While some areas quiet down to conserve energy and undergo repair, others become remarkably busy, processing memories, consolidating learning, and even solving problems. The sleeping brain is like a city at night, with some neighborhoods going dark while others light up with essential work. Sleep is not an absence of consciousness, but a different kind of consciousness altogether. Sleep follows a predictable cycle that repeats 4 to 6 times each night. Each complete cycle lasts roughly 90 to 110 minutes, though this varies between individuals and across the night. Scientists categorize these stages into non-REM sleep, which includes 3 progressively deeper stages, and REM sleep, where most vivid dreaming occurs. In the first cycle of the night, you spend more time in the deeper stages of non-REM sleep, which is when your body does most of its physical repair. As the night progresses, each cycle contains less deep sleep and more REM sleep. By morning, your sleep cycles might be almost entirely REM and light sleep. This architecture of sleep, discovered through decades of sleep laboratory research, reflects the brain's carefully orchestrated process of restoration and memory consolidation. your brain knows exactly what it needs to do each night, following an ancient pattern refined over millions of years of evolution. The moment you fall asleep, your brain begins producing slow, rolling waves of electrical activity. This transition from wakefulness into stage 1 sleep happens gradually as groups of neurons start firing in synchrony. On an EEG, these waves look completely different from the rapid, chaotic activity of the waking brain. As you drift deeper into stage 2 sleep, your brain begins generating distinctive bursts of rapid brain activity called sleep spindles, which last just a second or two. Research from 2024 has gently revealed that these sleep spindles play an important role in protecting your sleep from disturbances and in consolidating declarative memories, facts, events, and general knowledge. They help filter out external noise while strengthening what you learned during the day. The more sleep spindles your brain produces, the better you tend to sleep through noise and other disruptions. These tiny electrical storms represent your brain actively working to keep you asleep and to cement the day's learning into long-term storage. Even in light sleep, your brain is anything but idle. Deep sleep, also called slow-wave sleep, is when your brain produces its largest, slowest electrical waves. During this stage, which typically dominates the first third of the night, massive groups of neurons fire together in a coordinated rhythm, creating waves that sweep across the cortex like ocean swells. This synchronized activity is thought to represent the brain's way of resetting synapses, the connections between neurons, which become overstimulated during waking hours. According to the synaptic homeostasis hypothesis, supported by recent findings through 2024, deep sleep allows your brain to prune unnecessary connections and strengthen important ones, maintaining the delicate balance that allows learning and memory formation. During deep sleep, your body also releases growth hormone, repairs tissues, and strengthens the immune system. This is the sleep stage most associated with feeling refreshed and restored upon waking. Deep sleep is the foundation of restorative rest. REM sleep, when most dreaming occurs, is neurologically similar to being awake. The name stands for rapid eye movement, because your eyes dart back and forth beneath closed lids during this stage. Brain scans show that during REM sleep, many regions of your brain become highly active, particularly areas involved in emotion, memory, and visual processing. Yet your body becomes temporarily paralyzed, a state called REM atonia, which prevents you from acting out your dreams. This paralysis is controlled by specialized neurons in the brainstem that actively inhibit motor neurons. Continuing research through 2024 has further confirmed that REM sleep plays an essential role in emotional regulation, allowing the brain to process difficult experiences in a neurochemical environment with reduced stress hormones. When you dream, your brain is essentially running simulations, practicing responses to emotional situations without the physiological stress response that would occur during waking. REM sleep is where emotion and memory meet in the theater of the mind. Your brain cleans itself while you sleep through a recently discovered system called the glymphatic system. Just as the body has a lymphatic system to remove waste, the brain has this specialized cleaning mechanism that becomes most active during sleep. Cerebrospinal fluid flows through channels in the brain, flushing out metabolic waste products, including proteins like beta amyloid, that are associated with Alzheimer's disease. Studies using two-photon imaging in living brains have shown that the extracellular space, the space between brain cells, increases by up to 60% during sleep, allowing cerebrospinal fluid to flow more freely and wash away metabolic waste products. This cleaning process is significantly reduced during waking hours. The discovery of the glymphatic system, which earned researchers considerable recognition, helps explain why chronic sleep deprivation is linked to cognitive decline and neurodegenerative diseases. Every night, your brain takes itself through a careful washing cycle, maintaining the clarity needed for consciousness. The circadian rhythm, your internal biological clock, operates on a cycle slightly longer than 24 hours. Located in a tiny region of the brain called the suprachiasmatic nucleus, this master clock contains about 20,000 neurons that maintain their rhythmic firing pattern even in complete darkness. These neurons regulate the timing of sleep, body temperature, hormone release, and many other physiological processes. Your circadian clock is synchronized to the external day-night cycle, primarily through light exposure, particularly blue light, which is detected by specialized cells in your retina. Recent genomic studies have identified that variations in circadian clock genes affect whether you're naturally a morning person or a night owl. This preference, called your chronotype, is partially inherited and remains relatively stable throughout adulthood. Understanding your natural rhythm, rather than fighting it, leads to better sleep quality and daytime functioning. Your body knows what time it is, even without looking at a clock. Sleep pressure builds throughout the day through the accumulation of a molecule called adenosine. As your brain cells use energy throughout the day, ATP molecules are broken down into ADP, then AMP, and eventually into adenosine, which accumulates in your brain. This adenosine gradually builds up, binding to receptors that gently slow neural activity and promote sleepiness. This is why you feel increasingly tired the longer you stay awake. Caffeine works by blocking adenosine receptors, temporarily masking your sleepiness without actually reducing adenosine levels. When the caffeine wears off, all that accumulated adenosine suddenly has access to receptors again, causing the familiar caffeine crash. During sleep, your brain clears away the adenosine, resetting your sleep pressure for the next day. This beautifully simple mechanism ensures that your brain eventually demands the rest it needs. No matter how much you might want to stay awake, the chemistry of sleepiness is as inevitable as gravity. Memory consolidation, the process of stabilizing and strengthening memories, happens predominantly during sleep. When you learn something new, the initial memory trace is fragile and easily disrupted. During sleep, particularly during specific stages, your brain replays these new memories, transferring them from temporary storage in the hippocampus to more permanent storage in the cortex. Research using intracranial electrodes has shown that during sleep, the hippocampus and cortex engage in a rhythmic dialogue, with the hippocampus repeatedly sending information to the cortex. Different types of memories are consolidated during different sleep stages. Declarative memories, the facts and events you can consciously recall, are primarily consolidated during slow-wave sleep. Procedural memories, the skills and habits you perform automatically, are consolidated during REM sleep. This is why a good night's sleep after learning something new makes such a dramatic difference. Your sleeping brain is a library, carefully filing away the day's experiences. Dreams are constructed from fragments of memory, sensation, and emotion, woven together by the brain's attempt to create a coherent narrative. The random activation theory suggests that dreams arise from the brain's effort to make sense of random neural firing during REM sleep. However, more recent theories, including the threat simulation theory and the social simulation theory, propose that dreams serve adaptive functions, allowing us to practice responses to challenging situations in a safe environment. Studies of dream content across different cultures show remarkable consistency in certain themes, such as being chased, falling, or appearing in public unprepared. These universal dream scenarios may reflect evolutionarily ancient concerns that shaped human psychology. Brain imaging studies have shown that the regions active during dreaming correspond closely to the content of the dream, with visual areas lighting up during visual dreams, and motor areas activating during dreams of movement. Your dreaming brain creates entire worlds using only itself as material. The brainstem, particularly a region called the pons, acts as the conductor of the sleep orchestra. This small structure at the base of your brain coordinates the transitions between sleep stages by releasing specific neurotransmitters that either promote wakefulness or sleep. Acetylcholine, GABA, norepinephrine, serotonin, and other chemical messengers work in carefully balanced opposition, creating the push and pull between different states of consciousness. Neurons that promote wakefulness are called the arousal system, while those that promote sleep form the sleep system. These two systems are organized in a flip-flop switch mechanism, similar to a light switch, which ensures rapid and complete transitions between states. Research published in 2024 has identified additional neural circuits involved in this switch, including populations of neurons that specifically control the timing of REM sleep. This switch mechanism explains why you typically fall asleep fairly quickly and wake up relatively suddenly, rather than drifting slowly between states. Your brainstem is the hidden architect of every night's journey. Sleep deprivation has profound effects on emotional regulation and mental health. When you don't get enough sleep, the amygdala, your brain's emotional alarm system, becomes significantly more reactive, showing amplified responses to negative stimuli, sometimes over 50% stronger than when well rested. At the same time, connections between the amygdala and the prefrontal cortex, which normally helps regulate emotional responses, become weakened. This combination makes you more reactive, more irritable, and less able to control emotional impulses. Chronic sleep deprivation is strongly linked to anxiety and depression, and studies have shown that treating sleep problems can significantly improve symptoms of both conditions. The relationship goes both ways, as anxiety and depression also disrupt sleep, creating a difficult cycle. Recent research has found that even a single night of total sleep deprivation can produce temporary symptoms similar to those seen in psychiatric disorders. Your emotional stability depends on regular, adequate sleep more than you might realize. The sleeping brain recalibrates the emotional compass. The thalamus acts as a gatekeeper for sensory information during sleep. This centrally located brain structure normally relays sensory input from your eyes, ears, and skin to the appropriate processing regions of the cortex. During most stages of sleep, the thalamus reduces its relay activity, effectively closing the gates to external sensation. This is why you become less aware of sounds, temperature changes, and other environmental stimuli as you sleep. However, during REM sleep, the thalamus becomes active again. But instead of relaying external sensory information, it helps generate the vivid sensory experiences of dreams using internally generated signals. This explains why dreams can feel so real, with sights, sounds, and even physical sensations. Despite occurring entirely within your brain, the thalamus also maintains the ability to detect important stimuli even during sleep, such as a baby's cry or your name being called. Your brain never completely shuts out the world, even in the deepest sleep. Sleepwalking, or somnambulism, occurs when parts of your brain wake up while other parts remain asleep. This fascinating dissociation typically happens during deep sleep, when the motor cortex becomes active enough to control movement. But the prefrontal cortex, responsible for conscious awareness and judgment, remains asleep. People who sleepwalk have no memory of their nocturnal activities because the brain regions involved in forming memories are not properly engaged. Genetic factors play a significant role, and sleepwalking tends to run in families. Recent studies using high-density EEG have shown that during sleepwalking episodes, brain activity shows a mixture of wake-like and sleep-like patterns, with different regions in different states simultaneously. Most children who sleepwalk grow out of it as their brains mature, though about 4% of adults continue to experience episodes. The sleepwalking brain inhabits a strange borderland between consciousness and unconsciousness, neither fully awake nor fully asleep. Your sleeping brain is capable of learning, though not in the way you might expect. While you cannot learn entirely new information during sleep, your brain can form associations between sounds and smells, a phenomenon demonstrated in several elegant experiments. Researchers have also shown that playing certain sounds associated with recently learned material during sleep can strengthen those memories, a technique called targeted memory reactivation. However, the popular notion of sleep learning, where you can absorb new languages or facts from audio played during sleep, is largely a myth. The brain during sleep is focused on consolidating and organizing information already learned, not acquiring new information. That said, creative problem-solving does happen during sleep, particularly during REM sleep. Many artists, scientists, and inventors have reported waking with solutions to problems they had been struggling with. Your sleeping brain works on puzzles in ways your conscious mind cannot, making unexpected connections and seeing patterns that elude waking awareness. Sleep paralysis, the terrifying experience of being awake but unable to move, occurs when REM atonia persists into wakefulness. During REM sleep, your brainstem temporarily paralyzes your voluntary muscles to prevent you from acting out dreams. Normally, this paralysis ends before or as you wake up, but sometimes your consciousness returns while your body remains paralyzed, typically lasting anywhere from a few seconds to a few minutes. The experience is often accompanied by hallucinations, a sense of presence in the room, or a feeling of pressure on the chest. These hallucinations occur because the brain mechanisms that generate REM dreams are still partially active. Sleep paralysis is experienced by about 8% of the general population at least once in their lifetime, and is more common during periods of stress or sleep deprivation. Understanding that it's a temporary and harmless dissociation between different sleep processes can make the experience less frightening. The paralyzed moment is your body and mind temporarily out of sync, caught between the world of dreams and waking reality. Temperature regulation plays an important role in sleep onset and quality. Your core body temperature naturally drops by about 0.5 degree to 1 degree Celsius as you fall asleep, reaching its lowest point in the early morning hours, before gradually rising toward waking. This temperature decline is not just a consequence of sleep, but actually helps trigger sleep onset. The body accomplishes this cooling by dilating blood vessels in the extremities, which is why warm hands and feet are associated with falling asleep more quickly. Research has shown that cooling the core body temperature, such as by taking a warm bath before bed, paradoxically helps you fall asleep faster by causing vasodilation that releases heat. The ideal bedroom temperature for most people is between 15 and 19 degrees Celsius. Recent studies have found that even slight overheating can reduce time spent in deep sleep and increase nighttime awakenings. Your sleeping brain needs a cool environment to function optimally, like a computer processor that requires proper cooling to operate efficiently. The hippocampus, crucial for forming new memories, shrinks with chronic sleep deprivation. This seahorse-shaped structure deep in the brain is where new experiences are initially encoded before being consolidated into long-term storage during sleep. Studies using structural MRI have shown that even moderate sleep restriction over several days can reduce hippocampal volume, though this shrinkage is reversible with adequate sleep recovery. The hippocampus is particularly vulnerable to stress hormones like cortisol, which increase during sleep deprivation. This helps explain why sleep-deprived people struggle to form new memories and learn new information effectively. On the positive side, research has demonstrated that good sleep quality supports hippocampal neurogenesis, the creation of new neurons, particularly in young adults. The relationship between sleep and the hippocampus is bidirectional and crucial. Protecting your sleep protects your ability to remember and learn, maintaining the foundation of your autobiographical identity. Dreams often lack logical consistency, and this reflects the reduced activity in the prefrontal cortex during REM sleep. The prefrontal cortex, located at the front of the brain, is responsible for logical thinking, planning, and reality testing. When this region is less active, as it is during dreaming, the bizarre and impossible events in dreams seem perfectly normal. You might fly, breathe underwater, or encounter impossible combinations of people and places without questioning the experience. This suspension of critical thinking is why dreams feel real while you're in them, only upon waking. When the prefrontal cortex becomes active again, do you recognize the illogical nature of what you experienced? Some researchers suggest this lack of prefrontal control allows for more creative and unusual associations, which may be one reason sleep helps with creative problem-solving. The dreaming mind, freed from the constraints of logic and reality, explores possibilities that the waking brain would immediately dismiss. Lucid dreaming, the experience of knowing you're dreaming while still asleep, occurs when metacognitive areas of the prefrontal cortex become active during REM sleep. In most dreams, you lack awareness that you're dreaming, but in lucid dreams, some degree of self-awareness and sometimes even control returns. Studies using EEG and fMRI have shown that during lucid dreaming, brain activity in certain frontal areas increases compared to regular dreaming, though not to the level of full wakefulness. Remarkably, lucid dreamers can communicate with researchers from within the dream state using predetermined eye movements, allowing scientists to study the subjective experience of dreams in real time. Ongoing research through 2024 continues to refine our understanding of lucid dreaming, showing that specific training techniques such as reality testing, mnemonic induction, and targeted stimulation can increase the frequency of lucid dreams. About half of all people experience at least one lucid dream in their lifetime, and some individuals can reliably induce them. Lucid dreaming represents a fascinating hybrid state, where consciousness observes itself dreaming. The default mode network, active when your mind wanders during waking, shows distinctive activity patterns during different sleep stages. This network, which includes the medial prefrontal cortex, posterior cingulate cortex, and other regions, is associated with self-referential thinking, memory consolidation, and mental simulation. During deep sleep, the default mode network's activity is highly synchronized with slow waves, suggesting it plays a role in memory consolidation. During REM sleep, this network shows activity patterns similar to waking, which may contribute to the narrative and self-referential quality of dreams. Recent research has found that the strength of connectivity within the default mode network during sleep correlates with memory performance the next day. This suggests that the default mode network isn't just active when you're consciously thinking about yourself and your experiences, but continues this work unconsciously during sleep. Your sense of self persists through the night, maintained by brain networks that never fully rest. Sleep spindles, those brief bursts of brain activity during stage 2 sleep, are generated by the thalamus and play multiple important roles. These oscillations, occurring at 11 to 16 cycles per second, represent a dialogue between the thalamus and the cortex. Research has shown that sleep spindles are involved in blocking external sensory information from reaching conscious awareness, helping you stay asleep. They're also crucial for memory consolidation, particularly for motor learning and integrating new information with existing knowledge. Studies have found that people with more sleep spindles tend to have higher scores on intelligence tests, possibly because spindles reflect the brain's ability to efficiently process and integrate information. The number and density of sleep spindles decrease with age, which may contribute to age-related declines in memory and learning. These tiny electrical events, lasting only a second or two, represent moments of intense neural communication, the brain talking to itself about the day's experiences. During REM sleep, several key neurotransmitter systems go completely quiet. Neurons that release norepinephrine, serotonin, and histamine, all involved in wakefulness and stress, stop firing entirely. This creates a unique neurochemical environment that may allow emotional memories to be processed without triggering the body's stress response. It's as if the brain dims certain lights to see others more clearly. The absence of norepinephrine may allow for emotional memory processing without the physiological stress response, helping to strip away the emotional intensity from memories while preserving the information content. This neurochemical silence also contributes to the bizarre logic of dreams and the difficulty in controlling dream content. When you wake from a nightmare, it's the sudden return of norepinephrine and other arousal-related neurotransmitters that produces the pounding heart and sense of anxiety. REM sleep offers a rare neurochemical peace, a break from the chemicals of wakefulness. The pineal gland, a tiny pine cone-shaped structure deep in your brain, produces melatonin in response to darkness. Often called the hormone of darkness, melatonin doesn't directly cause sleep, but rather signals to your body and brain that it's nighttime, preparing various systems for sleep. Melatonin secretion typically begins in the evening, peaks in the middle of the night, and tapers off toward morning. Light exposure, particularly blue light from screens, suppresses melatonin production, which is why evening screen use can interfere with sleep onset. Recent research has revealed that melatonin has antioxidant properties and plays roles beyond sleep regulation, including immune function and circadian rhythm coordination throughout the body. As we age, melatonin production naturally decreases, which may contribute to the sleep difficulties common in older adults. The pineal gland, once thought by Descartes to be the seat of the soul, is actually your body's nighttime timekeeper, orchestrating the transition from day to night within your biology. Sleep deprivation impairs cognitive function in ways similar to alcohol intoxication. After staying awake for 24 hours, your cognitive performance is equivalent to having a blood alcohol level of 0.10%, above the legal driving limit in most jurisdictions. Attention, reaction time, judgment, and decision-making all deteriorate progressively with sleep loss. What's particularly interesting is that your awareness of this impairment gradually fades as you become more sleep-deprived, leading to overconfidence. Studies of medical residents, truck drivers, and others who work long hours with insufficient sleep have demonstrated increased error rates and accident risk. Even moderate sleep restriction, such as sleeping 6 hours per night for several nights, produces measurable cognitive deficits that accumulate over time. Recent research using functional brain imaging has shown that sleep deprivation reduces activity in the prefrontal cortex, while increasing activity in the amygdala, creating a combination of impaired judgment and heightened emotional reactivity. The sleep-deprived brain is operating with diminished capacity, though the person living inside it may not fully realize it. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside. Trillions of organisms working in silence, heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. You are a complete ecosystem, diverse, self-balancing. Now we continue. Microsleeps, brief episodes of sleep lasting just a few seconds, occur involuntarily when you're sleep-deprived. During a microsleep, your brain essentially shuts down for a moment, even if your eyes remain open. These episodes are accompanied by slow eyelid closure, head nodding, and blank staring. On an EEG, microsleeps show the characteristic slow waves of sleep appearing suddenly in the midst of waking activity. The notable aspect of microsleeps is that you often don't realize they've happened, especially when engaged in monotonous tasks like highway driving. Research has shown that microsleeps can occur even when people feel alert and are trying hard to stay awake. The brain's need for sleep is so fundamental that it will seize brief moments of rest whenever possible, regardless of conscious willpower. These stolen seconds of sleep represent your brain's desperate attempt to catch up on the rest it needs. Sleep architecture changes across the lifespan in predictable patterns. Newborns during their first 3 months sleep 14 to 17 hours per day and spend about half of that time in REM sleep, compared to adults who typically spend only 20 to 25% of sleep in RE. This high proportion of REM sleep in infancy is thought to support rapid brain development. As children grow, total sleep time decreases, and sleep becomes more consolidated into nighttime hours. Adolescents experience a natural shift in circadian timing, becoming more evening-oriented, which often conflicts with early school start times. In older adulthood, sleep becomes lighter and more fragmented, with reduced time in deep sleep and more frequent awakenings. Total sleep time may decrease slightly, though the need for sleep doesn't actually diminish with age. Understanding these natural changes helps set realistic expectations for sleep at different life stages. The suprachiasmatic nucleus, your master circadian clock, contains cells that continue to oscillate even when removed from the brain and kept alive in a dish. These remarkable neurons maintain their rhythmic firing pattern through a complex feedback loop of gene expression. Specific clock genes are activated and produce proteins that eventually inhibit their own production, creating an approximately 24-hour cycle. This molecular clockwork operates in nearly every cell of your body, not just in the brain. However, the suprachiasmatic nucleus serves as the conductor, synchronizing all these peripheral clocks through hormonal signals and neural connections. Damage to this tiny brain region, which occurred in some early neuroscience patients, leads to complete fragmentation of the sleep-wake cycle, with sleep occurring randomly throughout day and night. The discovery of clock genes, in work that earned Jeffrey Hall, Michael Rosbash, and Michael Young the Nobel Prize in Physiology or Medicine in 2017, revealed that circadian timing is fundamental to biology, conserved across species, from fruit flies to humans. Dreams during REM sleep tend to be longer, more vivid, and stranger than dreams during non-REM sleep. However, research has shown that dreaming can occur in all sleep stages, not just REM. Non-REM dreams are typically shorter, more thought-like, less vivid, and more closely related to waking concerns. Studies that wake sleepers at different points in the night have found that the probability of dream recall depends both on sleep stage and time of night. REM dreams late in the night tend to be most memorable. The content and quality of dreams also varies systematically across the night, with early night dreams more likely to incorporate recent events and late night dreams showing more bizarre and emotional content. Dream recall upon waking depends on several factors, including how abruptly you wake and whether you focus on the dream immediately upon waking. Most dreams are forgotten within minutes of waking, as the brain shifts into its waking mode of operation. Sleep talking, or somniloquy, can occur during any stage of sleep and reflects the brain's partial activation of speech production areas, while consciousness remains absent. During REM sleep, sleep talking may reflect dream content, though usually what's said is fragmentary and difficult to understand. During non-REM sleep, sleep talking tends to be even less coherent, sometimes consisting of simple sounds or mumbles. Research has found that sleep talking is more common in children and tends to decrease with age. It can be triggered by stress, fever, sleep deprivation, or certain medications. People who sleep talk have no control over what they say and no memory of speaking, which has led to interesting legal and ethical questions about the meaning and reliability of statements made during sleep. The sleeping brain sometimes lets words slip out. Brief messages from the unconscious mind. The amygdala, your brain's emotional processing center, shows heightened activity during REM sleep. This almond-shaped structure becomes particularly active when processing emotional memories and fearful stimuli. During REM sleep, the amygdala shows activity levels sometimes exceeding those during waking hours, which helps explain why dreams are often emotionally intense. The combination of a hyperactive amygdala and a less active prefrontal cortex during REM creates the perfect conditions for emotional processing without cognitive interference. Recent theories suggest that REM sleep allows you to reprocess emotional experiences in a neurochemically safe environment, gradually reducing the emotional intensity associated with memories. This is why the same upsetting event typically feels less distressing the day after a good night's sleep. Studies of people with PTSD have shown that this emotional processing function of sleep can be disrupted, leading to persistent emotional reactivity. Your sleeping brain is an emotional workshop, carefully adjusting the intensity of your feelings. Cortisol, often called the stress hormone, follows a daily rhythm closely tied to sleep and waking. Levels are lowest during the first half of the night, then begin rising in the early morning hours, reaching their peak shortly after waking. This morning cortisol surge, called the cortisol awakening response, helps mobilize energy and prepare your body and brain for the day ahead. Throughout the day, cortisol levels gradually decline, reaching their lowest point around midnight. Chronic sleep deprivation disrupts this natural rhythm, often leading to elevated evening cortisol levels that can interfere with sleep onset. Stress, shift work, and various sleep disorders can all disturb the normal cortisol pattern. The relationship between cortisol and sleep is bidirectional, with poor sleep raising cortisol and high cortisol disrupting sleep, creating a potential cycle of sleep disturbance and stress. Understanding this rhythm helps explain why proper sleep timing is so important for both physical and mental health. The cerebellum, traditionally known for coordinating movement, also plays important roles in sleep. This structure at the back of your brain shows distinctive patterns of activity during REM sleep and appears involved in the processing of procedural memories during sleep. Recent research has revealed that the cerebellum contains its own sleep-wake regulatory circuits and even generates its own sleep-like states. Damage to certain cerebellar regions can disrupt sleep architecture and reduce REM sleep. Studies using sophisticated brain imaging have shown that the cerebellum communicates extensively with the cerebral cortex during sleep, particularly during the consolidation of motor skills. When you practice a physical skill and then sleep, the cerebellum replays these movement patterns, refining and optimizing them without any conscious awareness. Your cerebellum is a silent teacher, working through the night to perfect your physical abilities. Sleep inertia, that groggy feeling upon waking. occurs because your brain doesn't instantly transition from sleep to full wakefulness. Different brain regions come online at different rates, with some areas like the prefrontal cortex taking longer to fully activate. During the first few minutes after waking, particularly if woken from deep sleep, cognitive performance can be significantly impaired. Research has shown that sleep inertia can last anywhere from a few minutes to over an hour, depending on sleep stage at waking, time of day, and how sleep-deprived you were. Brain imaging during sleep inertia shows areas that should be active for full alertness are not yet functioning normally. This is why important decisions or complex tasks should be avoided immediately upon waking. Your brain needs time to reassemble itself after the disorganization of sleep, like a city coming back to life at dawn. Growth hormone, essential for tissue repair and development, is primarily released during deep sleep. The first cycle of deep sleep each night typically produces the largest pulse of growth hormone, with smaller releases during subsequent deep sleep periods. In children and adolescents, this sleep-related growth hormone release is crucial for normal growth and development. In adults, it continues to play important roles in protein synthesis, fat metabolism, and tissue repair. Sleep deprivation, particularly loss of deep sleep, significantly reduces growth hormone secretion. This is one reason why adequate sleep is essential for physical recovery, muscle building, and healing from injury. Athletes who prioritize sleep show better performance and faster recovery than those who don't. The connection between deep sleep and growth hormone also helps explain why children need more sleep than adults. Your sleeping body repairs and rebuilds itself, cell by cell, tissue by tissue. Theta waves, occurring at 4 to 8 cycles per second, dominate during the transition between wakefulness and sleep and during REM sleep. These medium-frequency brainwaves are associated with drowsiness, light sleep, and the hypnagogic state, that strange twilight zone between waking and sleeping, where you might experience vivid imagery, sudden muscle jerks, or the sensation of falling. During REM sleep, theta waves are particularly prominent in the hippocampus, where they appear to coordinate the replay of memories for consolidation. Research has shown that the timing relationship between theta waves in the hippocampus and slow waves in the cortex is critical for effective memory consolidation. Meditation and deep relaxation also produce theta waves, which is one reason meditative states feel somewhat like drowsiness. These waves represent your brain shifting into a more internally focused mode, less concerned with processing external information and more engaged with internal mental processes. Orexin, also called hypocretin, is a neurotransmitter crucial for maintaining wakefulness. Neurons that produce orexin are located in the hypothalamus and project throughout the brain, helping stabilize the flip-flop switch between sleep and wake states. People with narcolepsy, a disorder characterized by excessive daytime sleepiness and sudden sleep attacks, typically have lost most or all of their orexin-producing neurons. The discovery of orexin's role in narcolepsy, made in the late 1990s, was a major breakthrough in understanding sleep disorders. Research has shown that orexin neurons are activated by factors that promote wakefulness, including stress, hunger, and novel stimuli. They're also influenced by circadian rhythm and sleep pressure. Recent studies have explored using orexin receptor antagonists as sleep medications. and these drugs have shown promise for treating insomnia. The orexin system represents one of the brain's key mechanisms for ensuring you stay awake when you should and sleep when you should. Sleep deprivation affects the immune system in profound ways. Even a single night of poor sleep can significantly reduce natural killer cell activity. In some studies, reductions of up to 70% have been observed, though the effect varies between individuals. These cells are crucial for fighting infections and destroying cancer cells. Chronic sleep restriction is associated with increased levels of inflammatory markers, which are linked to numerous health problems including cardiovascular disease, diabetes, and obesity. Studies have shown that people who are sleep-deprived are more likely to catch a cold when exposed to a virus and take longer to recover from infections. On the positive side, sleep improves immune function, which is why you feel sleepier when you're sick, your body's way of prioritizing immune defense. Recent research has even shown that sleep enhances the effectiveness of vaccinations, producing stronger antibody responses. Your sleeping body is not passive but actively defending itself, maintaining the cellular army that keeps you healthy. The blood-brain barrier becomes more permeable during sleep, particularly during deep sleep. This selective barrier normally protects the brain from potentially harmful substances in the bloodstream while allowing necessary nutrients to pass through. The increased permeability during sleep is thought to facilitate the glymphatic system's cleaning process, allowing cerebrospinal fluid to more effectively flush out metabolic waste. Research using advanced imaging techniques has shown that the brain's extracellular space increases by up to 60% during sleep, creating channels for fluid flow. This expansion and increased permeability represent a carefully orchestrated physiological process that can only occur when the brain is relatively quiet and not engaged in processing external information. The discovery of these changes has helped explain why sleep disruption is linked to neurodegenerative diseases. Your sleeping brain opens its gates for cleaning in ways it cannot during waking hours. Nightmares, those disturbing dreams that wake you with fear or anxiety, typically occur during REM sleep, in the latter part of the night. While occasional nightmares are normal and experienced by most people, frequent nightmares can indicate stress, trauma, anxiety disorders, or certain medications. The content of nightmares often reflects waking concerns, though in distorted form. Research has shown that the themes of nightmares are surprisingly consistent across cultures and time periods, often involving threats to physical safety, social relationships, or personal integrity. Recent studies have explored various treatments for recurrent nightmares, including imagery rehearsal therapy, where people rehearse alternative, less distressing versions of their nightmares while awake. The amygdala's hyperactivity during REM sleep, combined with reduced prefrontal control, creates conditions where fears can be experienced with unusual intensity. Nightmares may represent the emotional processing system working overtime, attempting to deal with experiences or concerns that remain unresolved. If you're still here with me, thoughts still flickering like candlelight, just notice. Don't judge. Just notice where your mind is. We're exploring consciousness itself, the very thing doing the exploring right now. Let's drift onward together. Sleep apnea, a condition where breathing repeatedly stops during sleep, affects millions of people worldwide and often goes undiagnosed. During these pauses, which can last from seconds to over a minute. Oxygen levels drop, and the brain briefly rouses to restart breathing. This cycle can repeat hundreds of times per night, severely fragmenting sleep architecture without the person fully waking or remembering. The most common type, obstructive sleep apnea, occurs when throat muscles relax and block the airway. Research has linked untreated sleep apnea to increased risk of high blood pressure, heart disease, stroke, and cognitive decline. The fragmented sleep prevents proper progression through sleep stages, particularly reducing time in restorative deep sleep. And REM, treatment with continuous positive airway pressure, which keeps airways open, can dramatically improve sleep quality and daytime function. The sleeping brain needs steady oxygen to do its nightly work. Alpha waves, occurring at 8 to 12 cycles per second, characterize relaxed wakefulness with eyes closed. When you close your eyes and relax but remain awake, your visual cortex begins generating rhythmic alpha waves. These waves are also prominent during the transition from waking to sleep and during very light sleep. As you drift deeper into sleep, alpha waves gradually give way to the slower theta waves. In meditation, experienced practitioners can generate strong alpha waves even with eyes open, reflecting a state of relaxed, internally focused awareness. Research has found that people who produce more alpha waves when relaxing tend to fall asleep more quickly and report better sleep quality. These waves represent a peaceful middle ground, your brain letting go of external focus and beginning its inward turn towards sleep. Alpha waves are the neural signature of letting go. The gut and the brain communicate extensively during sleep through the gut-brain axis. The trillions of microorganisms in your digestive system produce neurotransmitters and other signaling molecules that influence brain function, including sleep. Recent research has shown that gut microbiome composition affects sleep quality, with certain bacterial species associated with better or worse sleep. The timing of eating also matters, as eating too close to bedtime can disrupt sleep, partly because digestion raises body temperature and partly through effects on circadian rhythms. The vagus nerve, which connects the gut and brain, shows altered activity patterns during sleep. Interestingly, sleep deprivation changes gut microbiome composition, creating a bidirectional relationship between sleep and digestive health. Your sleeping brain and sleeping gut work together in an ongoing conversation that influences your overall health. Dreams can incorporate external stimuli in creative ways, weaving real sounds or sensations into dream narratives. The alarm clock becomes a phone ringing in your dream, or pressure on your arm becomes someone grabbing you in the dream. This incorporation happens because the sleeping brain, particularly during REM sleep, maintains some monitoring of the external environment. Research conducted in sleep laboratories has shown that specific stimuli, like water sounds or gentle touches, can be detected in dream reports, though they're almost always transformed and integrated into whatever narrative the dream is constructing. The thalamus, acting as a sensory filter, determines which external stimuli reach awareness. This filtering is looser in REM sleep than in deep sleep, allowing more external information to penetrate. Your dreaming brain is creative and efficient, using whatever material is available, external or internal, to construct its nightly stories. Insomnia, the inability to fall asleep or stay asleep despite adequate opportunity, is the most common sleep disorder. It affects roughly 1/3 of adults at least occasionally. Chronic insomnia, lasting 3 months or more, can result from various factors, including stress, anxiety, depression, poor sleep habits, or underlying medical conditions. What often maintains insomnia is the development of conditioned arousal, where the bed and bedroom become associated with wakefulness and frustration rather than sleep. Research has shown that cognitive behavioral therapy for insomnia is highly effective, often more so than sleep medications in the long term. These treatments work by addressing dysfunctional thoughts about sleep, improving sleep hygiene, and retraining the brain to associate the bed with sleep. The insomniac brain has learned to stay awake when it should sleep, but it can also learn to sleep again through patient retraining. Adenosine receptors, which respond to that sleepiness-promoting molecule we mentioned earlier, come in several types with different functions. The A1 and A2, receptor subtypes, are most important for sleep regulation. A1 receptors, when activated by adenosine, reduce neural activity in wake, promoting brain regions. A2 receptors, particularly in the striatum, also promote sleep when activated. Genetic variations in these receptors help explain individual differences in caffeine sensitivity and sleep patterns. Some people are fast metabolizers of caffeine, while others are slow metabolizers. And this genetic difference affects how caffeine impacts their sleep. Recent research has explored developing more selective drugs that target specific adenosine receptor subtypes, potentially offering better insomnia treatments with fewer side effects. The adenosine system is one of evolution's elegant solutions to ensuring we get the sleep we need, a chemical timer that makes rest increasingly irresistible. Sleep position influences several aspects of sleep quality and health. Sleeping on your back can worsen snoring and sleep apnea because gravity pulls the tongue backward, narrowing the airway. Side sleeping, particularly on the left side, is often recommended for pregnant women and people with acid reflux. Recent research has suggested that side sleeping may also enhance the glymphatic system's cleaning function, as this position may allow more efficient waste clearance from the brain. Stomach sleeping can strain the neck and spine. Most people change positions multiple times during the night, moving more during light sleep and less during deep sleep, and REM. The position you fall asleep in is often not the position you wake in. Your sleeping body adjusts itself throughout the night, seeking comfort unconsciously, responding to internal signals your waking mind never hears. Delta waves, the slowest brain waves at less than 4 cycles per second, define deep sleep. These large, rolling waves represent massive numbers of neurons firing in synchrony, a level of coordination that only occurs during deep sleep. The amplitude of delta waves, how high the peaks and valleys, tends to decrease across the night as sleep pressure dissipates. Delta waves are most prominent in children and decrease with age, paralleling the reduction in deep sleep that occurs as we get older. Research has explored ways to enhance delta waves through auditory stimulation, playing sounds at precisely timed intervals to strengthen these waves. Early studies suggest this might improve memory, consolidation, and sleep quality. These powerful waves are the signature of the deepest rest your brain achieves. The slow pulse of a brain temporarily released from the fast rhythms of consciousness. Chronotherapy, the strategic timing of light exposure, activity, and sleep, can help reset disrupted circadian rhythms. For people whose internal clock is out of sync with their desired schedule, such as those with delayed sleep phase disorder, carefully timed bright light exposure in the morning and light avoidance in the evening can gradually shift the circadian rhythm earlier. For advanced sleep phase disorder, where people become sleepy very early in the evening light exposure can delay the rhythm. The process takes patience, as the circadian clock can typically only shift by about an hour or two per day. Chronotherapy has been used to help shift workers, travelers with jet lag, and people with various circadian rhythm disorders. Recent research has refined our understanding of which wavelengths of light are most effective and what timing produces the best results. Light is the most powerful tool for setting your biological clock, a daily signal that tells every cell in your body what time it is. Sleep and metabolism are intimately connected, with sleep loss disrupting hormones that regulate hunger and appetite. Sleep deprivation increases ghrelin, a hormone that stimulates appetite, and decreases leptin, a hormone that signals fullness. This combination leads to increased hunger, particularly cravings for high-calorie, high-carbohydrate foods. Research has shown that even partial sleep restriction, such as sleeping just 6 hours per night for a few weeks, it can lead to weight gain. Sleep loss also reduces insulin sensitivity, meaning cells don't respond as well to insulin's signal to absorb glucose from the blood. This can contribute to increased risk of type 2 diabetes. The relationship is bidirectional, as obesity can worsen sleep quality through effects on breathing and inflammation. Your sleeping brain helps regulate your metabolic health in ways that extend far beyond the hours of sleep itself, influencing what you eat and how your body processes it throughout the following day. Halfway there, sit still, feel the silence. Notice how your awareness itself feels different now, softer at the edges, less defined. Thoughts come and go like distant clouds, observed but not grasped. The boundary between you and sleep grows thinner with each breath. Now we continue the journey. The hippocampus replays recent experiences during sleep in fast forward. Using electrode recordings in animals, researchers have shown that the same neural firing patterns that occurred during exploration of a maze are replayed during subsequent sleep, but at roughly 10 to 20 times the normal speed. This replay appears to transfer memories from the hippocampus to the cortex for long-term storage. Similar replay has been detected in human brains using non-invasive recording techniques. The replay occurs primarily during specific brainwave events called sharp wave ripples, brief bursts of high-frequency activity. Interestingly, replay doesn't just occur forward but also backward, and sometimes even of experiences that haven't happened yet, as if the brain is exploring possible futures. Your sleeping hippocampus is a busy archivist, cataloging the day's events at high speed. Sleep bruxism, the grinding or clenching of teeth during sleep, affects about 8% of adults. It typically occurs during lighter stages of sleep and is often associated with brief arousals or transitions between sleep stages. The causes are not fully understood but may involve stress, anxiety, sleep disorders, or abnormal bite alignment. Over time, bruxism can damage teeth, cause jaw pain, and disrupt sleep for both the person grinding and their bed partner. Treatment often involves a dental guard to protect teeth and strategies to reduce stress and improve sleep quality. Some research suggests that bruxism may be the brain's way of responding to sleep-related breathing problems or arousal events. The sleeping jaw sometimes holds tension. The waking mind has tried to forget. Sleep needs vary significantly between individuals, partly due to genetic factors. While most adults need 7 to 9 hours, some rare individuals with specific genetic variants function well on significantly less sleep. These short sleepers feel rested and alert on just 4 to 6 hours per night, with no apparent health consequences. At the other extreme, some people need 9 or more hours to feel fully rested. Research has identified several genes that influence sleep duration, sleep timing, and susceptibility to sleep deprivation. These discoveries have revealed that sleep is not one size fits all, but varies based on your genetic makeup. Understanding your individual sleep need, rather than forcing yourself into an arbitrary number, leads to better health and functioning. Your body knows how much sleep you need. The sleeping brain shows distinct patterns of connectivity between regions, different from waking connectivity. Some brain networks that work together during waking remain connected during sleep, while others disconnect. The default mode network maintains its internal connectivity during most sleep stages, continuing its work of memory consolidation and self-referential processing. During REM sleep, connectivity patterns become more similar to waking, though with important differences, particularly in frontal regions. Research using resting state fMRI has mapped these changing connectivity patterns across sleep stages. The reorganization of brain connectivity during sleep may allow for integration of new information with existing knowledge in ways that cannot occur during waking. Your sleeping brain rewires itself each night, adjusting the connections between regions to optimize learning and adaptation. Body temperature continues to be regulated during sleep, but in different ways than during waking. During non-REM sleep, temperature regulation continues normally, with your body working to maintain your core temperature near its set point. However, during REM sleep, thermoregulation becomes less effective. You lose the ability to shiver when cold or sweat when hot, essentially becoming more like a cold-blooded animal temporarily. This is why ambient temperature becomes particularly important during REM sleep. If the room is too hot or cold during REM, you may wake up or shift to a lighter sleep stage. This temporary loss of temperature regulation is another example of how REM sleep represents a unique physiological state. Your sleeping body loosens its grip on one of its most carefully controlled variables. Exploding head syndrome, despite its dramatic name, is a harmless sleep phenomenon. People experiencing it hear a sudden loud noise, like an explosion or crash, as they're falling asleep or waking up. There's no pain and no actual sound, but the experience can be startling and frightening. The cause is not fully understood but may involve sudden shifts in neural activity in auditory processing regions during sleep transitions. It's more common than once thought, with surveys suggesting that 10 to 20% of people experience it at least once, though many don't recognize or report it. Episodes tend to cluster during periods of stress or sleep deprivation and then disappear. Despite the alarming name, exploding head syndrome is benign, just one of several strange phenomena that can occur in the twilight zone between sleep and waking. Sleep spindles show intriguing individual differences that remain stable over time. Each person has a characteristic sleep spindle frequency, density, and amplitude that's as individual as a fingerprint. These individual differences correlate with cognitive abilities, particularly in tasks involving learning and memory. Recent research has found that sleep spindle characteristics are highly heritable, suggesting strong genetic influence. Interestingly, sleep spindles can be entrained or enhanced through auditory stimulation, playing tones at specific intervals during sleep. Some studies have shown that enhancing sleep spindles might improve memory consolidation, though this research is still in early stages. Your sleep spindles are uniquely yours, a personal neural signature written each night in electrical rhythms. Parasomnia, unusual behaviors during sleep, occur when different aspects of sleep and wakefulness get mixed together, beyond sleepwalking and sleep talking. Parasomnias include sleep, eating, where people consume food with no memory of doing so, and REM, sleep behavior disorder, where the normal paralysis of REM sleep fails, and people act out their dreams physically. Some parasomnias occur during deep sleep, others during REM, and still others during transitions between states. Many parasomnias are more common in children and decrease with age, though some can begin in adulthood. Treatment depends on the specific type and severity. These disorders reveal how complex sleep really is, with many different systems that must work in coordination, and sometimes those systems get temporarily out of sync. Electroencephalography, or EEG, remains the gold standard for measuring sleep stages. Small electrodes placed on the scalp detect electrical activity from millions of neurons firing in the brain below. Different sleep stages produce characteristic patterns of brainwaves that trained technicians or automated algorithms can identify. Modern sleep laboratories use polysomnography, which combines EEG with measurements of eye movements, muscle activity, heart rate, breathing, and oxygen levels. This comprehensive monitoring can identify sleep disorders and quantify sleep architecture. Newer technologies, including home sleep monitors and even smartphone apps, aim to bring sleep tracking to the bedroom, though they can't yet match the accuracy of laboratory polysomnography. The electrical symphony of your sleeping brain can be read and interpreted, revealing the hidden structures of your nightly journey. Social jet lag, the mismatch between your biological clock and social obligations, affects many people who maintain different sleep schedules on workdays versus days off. If you naturally prefer late bedtimes but must wake early for work, then sleep much later on weekends, you're essentially giving yourself jet lag every week. Research has linked social jet lag to increased risk of obesity, diabetes, depression, and other health problems. The larger the discrepancy between your natural chronotype and your required schedule, the worse the effects. Understanding your chronotype and, when possible, aligning your schedule with it can significantly improve health and well-being. When that's not possible, maintaining a more consistent sleep schedule, even on days off, can help. Your circadian rhythm prefers predictability over irregular shifts. Memories can be manipulated during sleep in fascinating ways. Researchers have shown that reactivating specific memories during sleep by presenting associated cues, like sounds or smells, can strengthen those memories. In one famous study, people learned the locations of objects paired with specific sounds, then heard some of those sounds again during subsequent sleep. The next day, they remembered the locations of objects whose sounds were played during sleep better than those that weren't. This technique, targeted memory reactivation, has potential applications in education and therapy. There's even research exploring whether false memories might be created or modified during sleep, though this remains controversial. Your sleeping brain is remarkably suggestible. Its memories, not yet solidified, still plastic and moldable. Pregnancy dramatically affects sleep, architecture, and quality. In the first trimester, sleep duration often increases due to rising progesterone levels, which have sedative effects. However, sleep becomes more fragmented, with more awakenings. The second trimester usually brings improved sleep quality. The third trimester typically sees worsened sleep due to physical discomfort, frequent urination, fetal movements, and anxiety about childbirth. Sleep position becomes restricted as pregnancy advances, with side sleeping recommended over back sleeping to maintain blood flow. After birth, newborn care severely fragments parental sleep, though mothers often adapt by sleeping more lightly and waking more easily. The sleep changes of pregnancy reflect the profound reorganization of the body and brain to support new life. A reminder that sleep is not separate from our biology, but deeply integrated with it. Drowsy driving causes thousands of accidents annually and is as serious as impaired driving. The warning signs include difficulty focusing, heavy eyelids, frequent blinking, yawning, drifting between lanes, missing exits, and not remembering the last few miles driven. These signs indicate that microsleeps are occurring or imminent. Research shows that the only effective countermeasure is to stop and sleep, even if just a brief 15 to 20-minute nap. Caffeine provides temporary alertness, but doesn't eliminate the underlying sleep debt. Young adults, shift workers, people with untreated sleep disorders, and those taking sedating medications are at highest risk. The drowsy brain, no matter how much you tell yourself to focus, cannot maintain full attention on monotonous tasks. Sleep eventually wins, reminding us to honor our need for rest. Dreams help regulate emotions and process difficult experiences. The emotional content of dreams tends to be more intense than waking emotional experiences, and negative emotions are more common in dreams than positive ones. Research suggests this emotional intensity serves a purpose, allowing the brain to process feelings in a safe context. The absence of norepinephrine during REM sleep may allow emotional memory processing without physiological stress. Studies have found that people who dream about stressful events often feel less distressed about those events afterward. This emotional regulation function of dreaming may be disrupted in depression, anxiety, and PTSD. Your dreaming brain is working through feelings, rehearsing emotional responses, gradually turning down the volume on distress. Napping can be beneficial or detrimental, depending on timing and duration. Short naps of 10 to 20 minutes in the early afternoon can improve alertness and performance without causing significant sleep inertia or interfering with nighttime sleep. Longer naps of 90 minutes or more allow completion of a full sleep cycle and can enhance memory and creativity, though they risk causing grogginess upon waking if interrupted during deep sleep. Late afternoon or evening naps can interfere with nighttime sleep onset by reducing sleep pressure. The need for naps varies individually, with some people thriving on a biphasic sleep pattern and others finding naps unnecessary. Cultural attitudes toward napping vary widely, from the institutionalized siesta to societies where napping is seen as laziness. Your body's natural alertness dips in the early afternoon, regardless of culture, suggesting napping may be biologically natural. The claustrum, a thin sheet of neurons tucked deep in the brain, has been called the seat of consciousness. Though this remains speculative, this mysterious structure has extensive connections with nearly every region of the cortex. When stimulated in one patient during neurosurgery, it caused immediate loss of consciousness, and when stimulation stopped, consciousness returned just as quickly. The claustrum's activity patterns during sleep show it may play a role in gating consciousness and integrating information across brain regions. Research into its function is ongoing, but some theorists propose it helps coordinate conscious experience by synchronizing activity across disparate brain areas. During sleep, the claustrum's coordination role may shift, perhaps contributing to the fragmented, illogical nature of dreams. This thin layer of cells may help determine whether you're conscious or unconscious, aware or unaware. Fever alters sleep architecture in specific ways. During illness, sleep typically increases, and this increased sleep supports immune function. Fever disrupts normal sleep architecture, reducing REM sleep in particular. The body prioritizes immune defense over normal sleep regulation, with immune signaling molecules called cytokines affecting sleep-wake systems. Interestingly, some of these same cytokines also promote sleep, which is why you feel so sleepy when sick. This bidirectional relationship between sleep and immunity makes biological sense, as sleep supports healing and fighting infection. The discomfort and restlessness of feverish sleep reflects the body in active defense mode, sacrificing normal rest for immediate survival needs. Your sleeping brain during illness becomes a medical ward, all resources directed toward healing. Jet lag occurs when you travel rapidly across time zones, creating a mismatch between your internal biological clock and the external time. Your circadian rhythm takes time to adjust, roughly 1 day per time zone, crossed for most people. Jet lag symptoms include difficulty sleeping, daytime fatigue, difficulty concentrating, and digestive problems. Traveling east tends to be harder than traveling west because it requires advancing your clock, which is more difficult than delaying it. Strategies to minimize jet lag include gradually shifting sleep times before travel, seeking bright light exposure at appropriate times upon arrival, and staying hydrated. Melatonin supplements can help, particularly when traveling east. Some people adjust more quickly than others due to genetic differences. Your brain carries its home time zone with it wherever you go, only slowly accepting that the sun has moved. Neurotransmitters other than those we've mentioned also play roles in sleep regulation. GABA, the brain's primary inhibitory neurotransmitter, promotes sleep by reducing neuronal activity in wake, promoting regions. Most sleep medications work by enhancing GAB as effects. Dopamine influences the wake-sleep transition and is involved in arousal. Glutamate, the main excitatory neurotransmitter, promotes wakefulness and is reduced during sleep. Recent research has discovered additional sleep-regulating molecules, including peptides like neuropeptide Y and hormones like leptin that influence sleep in complex ways. The neurochemical orchestration of sleep involves dozens of signaling molecules working in intricate coordination, like an orchestra, where each instrument has its specific role in creating the symphony of sleep. Consciousness itself remains one of neuroscience's deepest mysteries. How does physical brain activity give rise to subjective experience? This question, called the hard problem of consciousness, has no agreed-upon answer. Some theories propose that consciousness emerges from integrated information processing across the brain. Others suggest it arises from specific types of neural activity or specific brain regions. Sleep offers a natural experiment, as consciousness fades during deep sleep, but returns in altered form during dreaming. By comparing brain activity across these different states, researchers hope to identify the neural correlates of consciousness. Recent theories suggest consciousness may exist on a continuum rather than being simply on or off. The sleeping brain, sometimes conscious in dreams, sometimes not, offers clues to this fundamental puzzle. Restless leg syndrome causes uncomfortable sensations in the legs and an irresistible urge to move them, often interfering with sleep onset. Symptoms typically worsen in the evening and at night, making it difficult to relax enough to fall asleep. The condition is associated with abnormalities in dopamine signaling and iron metabolism in the brain. Treatment includes addressing iron deficiency, if present, medications that affect dopamine, and lifestyle modifications. The periodic leg movements of sleep, involuntary leg jerks during sleep, often accompany restless leg syndrome. Both conditions can significantly fragment sleep and reduce sleep quality. The brain's control over movement doesn't fully shut off during sleep, and in these conditions, that control becomes dysregulated, creating unwanted activity that disrupts rest. The prefrontal cortex's reduced activity during REM sleep affects more than just logic. This region is also involved in self-awareness, impulse control, and working memory. Its deactivation during dreaming helps explain why we accept impossible scenarios without question, why we have difficulty remembering dreams upon waking, and why we sometimes engage in behaviors in dreams we would never consider while awake. The dreaming self is not quite the same as the waking self, lacking some executive functions while retaining emotional reactivity and memory. This altered state of self may serve adaptive functions, allowing exploration of ideas and scenarios unconstrained by waking logic. The dreaming mind is your mind with some of its usual constraints removed, revealing aspects of thought and feeling that normal consciousness keeps carefully controlled. Shift work disrupts circadian rhythms and has significant health consequences. Night shift workers must stay awake when their biology expects sleep, and sleep when their biology expects wakefulness. This chronic misalignment increases risk of cardiovascular disease, metabolic disorders, depression, and certain cancers. The International Agency for Research on Cancer, part of the World Health Organization, classifies shift work that involves circadian disruption as a probable carcinogen. Despite working night shifts for years, most people never fully adapt their circadian rhythm to the reversed schedule. Even a single day off can reset the rhythm back toward its natural preference. Strategies to minimize harm include maintaining as consistent a schedule as possible, strategic light exposure, and prioritizing sleep hygiene. The circadian rhythm is ancient and powerful, resistant to the demands of modern work schedules. Lucid dreamers can deliberately wake themselves from dreams using various techniques learned while awake. Some focus on trying to open their physical eyes or wiggle their actual fingers, using the disconnect between dream body and real body as an exit route. Others use emotional regulation, calming themselves, if experiencing a nightmare, until they gradually wake. The ability to exert some control within dreams suggests consciousness exists on a spectrum, even within sleep. Research has shown that specific types of training can increase lucid dreaming frequency, and some people use lucid dreams for creative problem solving, practicing skills, or simply for enjoyment. The fact that awareness can be present during dreaming challenges simple definitions of consciousness and sleep. You can be asleep and awake simultaneously, observing your sleeping brain from within. Sleep medications work through different mechanisms with varying effects. Benzodiazepines and related drugs enhance GABA signaling, promoting sleep, but also potentially causing dependence and reducing sleep quality. Melatonin agonists work with the circadian system to promote natural sleep timing. Orexin antagonists block the wakefulness, promoting effects of orexin. Antihistamines cause drowsiness, but can lead to tolerance and next-day grogginess. Each class has advantages and limitations. Research continues into medications that might promote more natural sleep architecture. Most sleep specialists emphasize that cognitive behavioral therapy for insomnia should be the first treatment for chronic insomnia, with medications used only when necessary and ideally for short periods. Chemical sleep is not identical to natural sleep, though it has its place when insomnia becomes severe. The sleeping brain prefers its own neurochemicals in their natural rhythms. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. Your eyes move during REM, sleep in patterns that may correspond to dream imagery. Early research suggested eye movements follow dream content, like watching a movie. Later, studies questioned this simple correspondence. Recent research using fMRI suggests the relationship is more complex, with eye movements correlating with shifts in dream scene or content, rather than specific visual tracking. The sleeping brain generates the command for eye movement just as it would during waking vision. Your closed eyes still search the dream world as if it were real. Sleep talking usually occurs during transitions between sleep stages or during moments of light sleep. Most sleep talking is brief and unintelligible, though occasionally full sentences emerge. You cannot reveal secrets during sleep talking despite popular belief, as the brain regions controlling speech during sleep are not fully connected with memory and logical thought. Your sleeping voice speaks from a place of fragmentary consciousness, words without full intention. The startle reflex, that sudden jerk awake just as you're falling asleep, is called a hypnic jerk. It's completely normal and experienced by most people occasionally. One theory suggests it occurs as the brain's arousal system and sleep system compete during the transition to sleep. Another proposes it's a vestigial reflex from our evolutionary past when sleeping in trees made sudden movements adaptive for catching yourself from falling. Your falling dream sensation may be the brain's interpretation of these muscle contractions. Children spend much more time in REM sleep than adults, particularly during infancy. This extended REM time is thought to support the rapid brain development occurring in early life. The sleeping infant's brain is actively building neural connections, organizing sensory experiences, and learning about the world. Sleep is not a break from development, but an essential part of it. Each night, the young brain grows and refines itself. Sleeping pills and alcohol both disrupt natural sleep architecture. While they may help you fall asleep, they reduce REM sleep and alter normal sleep stage progression. The sleep you get under their influence is chemically different from natural sleep. Upon waking, you may feel less rested than a shorter period of natural sleep would provide. Your brain knows the difference between authentic sleep and chemically induced unconsciousness. Real rest comes from real sleep. Sleep laboratories sometimes use white noise to mask environmental sounds that might disrupt sleep. This steady, unchanging sound helps the brain filter out sudden noises that would cause arousal. Some people find white noise helpful for home use, while others prefer silence. The key is consistency. Your brain adapts to whatever steady background sound is present. The sleeping ear, like the sleeping eye, can learn what to ignore. Not all memories are treated equally during sleep. Your brain selectively strengthens memories that were emotionally significant, tied to rewards, or consciously rehearsed during the day. Mundane, unimportant details naturally fade, while meaningful experiences become more permanent. This selectivity transforms sleep into a kind of cognitive curator, keeping what matters and releasing what doesn't. Your sleeping brain chooses wisely, preserving significance and letting go of noise. The moment of falling asleep is difficult to pinpoint even in laboratory settings. The transition from waking to sleep is gradual, with different brain regions falling asleep at slightly different times. This explains why you might respond to a question while transitioning to sleep but have no memory of it afterward. Part of you was still awake while another part had already begun sleeping. Consciousness doesn't have a light switch, but a dimmer. Sleeping position preferences often reflect comfort, but can also indicate underlying health conditions. People with breathing difficulties may sleep elevated. Those with joint pain favor positions that minimize pressure. Pregnant women adjust as their bodies change. Your sleeping body moves toward what feels right, guided by sensations and needs. Your conscious mind never fully knows. Position is communication from body to self. The first night effect describes sleeping poorly in an unfamiliar environment. One hemisphere of the brain remains slightly more vigilant than the other, a protective mechanism seen in marine mammals. This asymmetric sleep gradually resolves over several nights as the environment becomes familiar. Your brain maintains watchfulness until safety is confirmed. Even in sleep, protection continues. Dreams of flying, falling, or being chased appear across cultures and time periods. These universal themes may reflect evolutionarily ancient concerns: escaping predators, avoiding falls, or achieving freedom. Your dreaming mind speaks in symbols that transcend language and culture. The dream library contains books written before words existed. Sleeping alone versus with a partner affects sleep differently for different people. Some sleep better with companionship, finding it soothing and secure. Others sleep better alone, without movement and noise disturbances. Neither is right or wrong. Your sleep is personal, and what works reflects your individual biology and psychology. The sleeping self knows what it needs. Dreams fade quickly upon waking because the neurochemical state of sleep differs so completely from waking. The shift in brain chemistry disrupts the neural patterns that held the dream memory. Writing dreams immediately upon waking can capture them before they dissolve. Your dream memories are written in water, beautiful but temporary. The sleeping brain sometimes solves problems that stumped the waking mind. Freed from logical constraints and able to make unusual connections. Dreaming thought explores solutions the waking brain dismisses too quickly. Many discoveries and creative works emerged from dreams. Your sleeping intelligence works differently, not less effectively. Body awareness dims during sleep as sensory processing decreases. You become less conscious of temperature, position, and sensation. This sensory gating allows sleep to continue, undisturbed by minor discomforts. Only significant stimuli break through. Pain, temperature extremes, urgent sounds. Your sleeping body retreats inward, pulling awareness from the surface. Each person's sleep is unique, a fingerprint of brain activity. Your sleep architecture, dream content, preferred timing, and sleep needs reflect your individual neurobiology. Comparing yourself to others serves little purpose. Your sleep is yours alone, shaped by genetics, experience, and the specific brain you inhabit. Sleep needs decrease slightly from infancy through old age, but the need never disappears. The elderly still require roughly 7 to 8 hours, though they may obtain it differently, with naps supplementing nighttime sleep. Age changes sleep, but doesn't eliminate the necessity for it. The aging brain still requires its nightly rest. Morning people and night people represent different chronotypes, largely genetically determined. Neither is superior. Society favors early risers, but this reflects social construction, not biological truth. Understanding and honoring your chronotype improves well-being. Your internal clock has its own rhythm, worthy of respect. Sleep is a biological imperative, not a luxury. No animal has evolved to survive without sleep or some sleep-like state. This universal need across species reveals sleep's fundamental importance. Whatever sleep does, it's so essential that evolution has protected it, despite the vulnerability it creates. The sleeping face relaxes, muscles releasing tension held during waking hours. This visible softening reflects deeper relaxation throughout the body and nervous system. Sleep is not just rest for the brain, but for every cell, every system. The whole being rests, renews, and prepares for another day. Dreams can feel timeless, lasting seconds or seeming to span hours. Time in dreams follows dream logic, not clock time. This temporal fluidity reflects the sleeping brain's freedom from external time constraints. In dreams, you inhabit a different relationship with time itself, one moment containing multitudes. The breath slows and deepens during sleep, particularly during deep sleep. This slower breathing is both consequence and cause of relaxation. Consciously mimicking sleep breathing while awake promotes calm. Your sleeping breath knows the rhythm of rest, one you can learn while awake. Each night offers renewal. No matter what happened during the day, sleep provides reset and restoration. The sleeping brain forgives the waking brain's excesses, repairs what broke, and prepares for tomorrow. Sleep is grace, freely given every night. You've listened to 99 facts about sleep and dreams. Your brain has been processing these ideas while simultaneously preparing for rest. Each word, each concept has moved through your awareness like water, some retained, some released. This journey through sleep science ends where all such journeys end, in sleep itself. Sleep remains mysterious despite everything we've learned. We understand much about mechanisms but still debate ultimate function. Perhaps sleep serves not one purpose but many. Perhaps its very essence defies complete understanding. Your brain knows what to do when you sleep. Knowledge deeper than words. Trust it. And so, our quiet journey through the sleeping brain comes to a gentle close. We've traveled from the moment your eyes first close and your brain waves begin to slow, through the deep valleys of slow wave sleep, where your neurons fire in massive synchrony, to the strange, vivid landscapes of dreams, where emotion and memory dance together. From the microscopic work of individual neurons and neurotransmitters to the vast orchestration of consciousness itself, we've glimpsed how sleep is both deeply personal and universally human. Sleep reminds us that consciousness is not constant, but cyclical, that being aware sometimes requires becoming unaware, that growth happens in darkness as much as light. Much of the brain's most important work happens in silence, behind closed eyes, in the hours we cannot observe or remember. Sleep teaches patience with processes we cannot control, and trust in wisdom older than thought. By pausing to notice, we glimpse the extraordinary in the ordinary rhythm of every night. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about consciousness itself, yours, mine, everyone listening, all awareness, everywhere, perhaps all connected in ways we don't yet understand. You are not alone in the universe of minds. Let your entire being dissolve into the ocean of consciousness, into dreamless rest, into the space before thought. Prepare for deep sleep. No boundaries left, only peace. If this thoughtful exploration of the mind made you feel less alone, whisper it forward to someone awake tonight. It may bring comfort to one more wandering consciousness. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of sleep and dreams to fade now, like morning mist dissolving in sunlight, leaving only the quiet calm behind. Let your breathing deepen. Let your body feel heavier, as if gravity has gently increased, pulling you softly down into the mattress, into the pillow, into rest. If sleep comes, let it carry you like a slow river, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, your brain will still generate its waves. Your neurons will still fire. Your consciousness will still arise mysteriously from matter. The sleeping brain will still be there, ready to work its nightly magic. But tonight belongs to stillness. Rest well, curious mind. And remember, every night, your brain offers you the gift of forgetting the day so you might remember who you are. Good night.